Physical quantities. Physical quantities, the building blocks of physics. Physics aims to unveil the secrets of the universe by analyzing natural phenomena and the relationships between the measurable quantities that characterize them. These quantities, defined as physical quantities, represent the pillars on which our understanding of the world is based. Table of contents: velocity, speed, acceleration, force, energy, momentum. A universe to discover. Physical quantities as keys to knowledge. Physical quantities play a fundamental role in all fields of physics. In mechanics, force, velocity, acceleration are essential for describing the motion of bodies as well as energy and momentum. In electromagnetism, electric charge, current, and voltage are the basis for the operation of electrical circuits and electronic devices. In thermodynamics, temperature, heat, and work are key quantities for understanding thermal energy transfers. Knowing and being able to correctly use physical quantity is a fundamental requirement for anyone who wants to undertake a scientific study path or to fully understand the natural phenomena that surround us. You'll answer to questions like this: why does an object fall down? How long it takes to reach the ground? Or this: why does the sun rise? Or this: why does ice float? And many others. Get ready to immerse yourself in the wonderful world of physics, where physical quantities will be your guides to unraveling the mysteries of universe. In particular, here we will focus on the meaning and understanding of some of the many physical quantities: speed, acceleration, force, energy, momentum.
Enough with senseless memorization. Instead, try to understand the logic behind physics. Velocity, force, energy, momentum. They're not just words for your homework. They explain everything from a sprinter's burst of speed to why you feel a jolt when a car stops abruptly. Grasp these concepts and you'll see the world with completely new eyes. Ready to dive in?
Scalar quantities and vector quantities, two sides of the same coin. Physical quantities are divided into two main categories. Scalar quantities represent entities that have only a numerical value and a unit of measurement. Examples of scalar quantities include mass, temperature, time, and density. In these quantities, direction plays no role. Vector quantities, in addition to the numerical value of unit of measurement, they also have a direction and a sense. To correctly display a vector quantity, it is necessary to use a vector, an arrow that indicates the direction and length proportional to the numerical value. Examples of vector quantities include velocity, force, displacement, and acceleration. Units of measurement, a universal language for science, to communicate the results of our measurements in a unique and precise way, it is essential to use a standardized system of units of measurement that is the International System of Units, SI. Speed and velocity. Speed is the distance traveled by a body and the time it takes to travel it. Velocity is the ratio between the difference of the position vectors of a body with respect to a reference system and the time taken in this movement. Note: speed can be considered a scalar quantity only in one-dimensional space, line. Speed is instead a vector quantity in two or more dimensional space. In two-dimensional space, x, y, it is not enough for me to know the speed to understand the movement of a body. I also need to know in which direction the body is moving. Acceleration. Acceleration is a vectorial physical quantity, which means it can be represented by a vector as it has magnitude, direction, and sense. Average acceleration measures the change in an object's velocity over a time interval. Therefore, it can be said that acceleration is directly proportional to the change in velocity and inversely proportional to the time taken. Average acceleration is given by instantaneous acceleration is the value of acceleration at a specific point in time and is obtained from the average acceleration by taking the time interval delta t to 0. Mathematically, it is considered the limit of the average acceleration as delta t tends to 0. Therefore, instantaneous acceleration is nothing more than the derivative of velocity with respect to time. Acceleration can be positive, negative, or zero. Positive acceleration. When positive, the object is increasing its speed, that is, it is moving faster. Negative acceleration. When acceleration is negative, the object is decreasing its speed, that is, it is slowing down. Zero acceleration. When acceleration is zero, the object is moving at the same speed, that is, it is moving at a constant speed. The unit of measurement for acceleration in the International System is the meter per second squared. This unit is derived from dividing velocity, measured in meters per second, by time, measured in seconds. Force. Force is what causes the state of motion on a free body to move in a state of rest. For example, the boat is free to move, but is stationary. The force on the wind can set it in motion. Force is what causes the change in trajectory or speed of motion or the state of rest. For example, the ball thrown towards a player is free in its flight, but their muscular force can deflect it, slow it down, or perhaps even stop it. Force is what causes a deformation of an object. For example, a can to which a force is applied greater than the necessary to support it. The force that pushes it can deform it. To describe a force in physics, it is necessary to specify, as for any vector quantity, its four characteristics: magnitude, the strength or intensity of the force, measured in units such as newtons, N, or pounds, lb; point of application, the specific point on the object where the force is applied; direction, the line along which the force acts, typically represented by an angle or a compass direction; sense of action, the direction in which the force is acting, such as left, right, up, or down. Since force is a vector quantity, it is represented with a capital letter surmounted by an arrow. The unit of measurement in the International System is the Newton, N. The measuring tool is the dynamometer. The greater the extension, the greater the force. Energy. Energy is the ability of a body to do work, that is, to move something or transform it. For example, we need energy to move furniture, to ride a bike, to grow, to cook an egg, to boil water, etc. Energy can manifest itself in different forms. The main ones are seven. Electrical energy. This is the energy we use to light our homes, run our computers, listen to music. Thermal energy is the heat that can be obtained by burning a fuel or by friction between two bodies, by passing hot water through a radiator, turning on an iron. Chemical energy is found in many substances, such as food and in materials that can be burned: wood, coal, gas, gasoline. Nuclear energy is contained in the nucleus of an atom. It is released as a result of nuclear reactions. Kinetic energy is the energy possessed by moving bodies. Potential energy is the energy due to the position occupied by a body. When an object at rest at a certain height h, with a given potential energy given by the product of its mass times the height h times the acceleration due to the gravity g, mgh, is dropped, its potential energy is converted into kinetic energy. Light energy is light of the sun, a lit candle, burning wood, lighting. Without light energy, plants will not carry out photosynthesis, and therefore there will be no life on Earth. The law of conservation of energy states that energy can neither be created nor destroyed. It can only be transformed from one form to another. For example, water at the top of a waterfall possesses potential energy. As it descends, the potential energy of the water is transformed into kinetic energy. In the hydroelectric power plants downstream of the waterfall, kinetic energy is transformed into electrical energy, or it can be transferred from one body to another, for example, from the foot to the ball, from the wind to the sail. The unit of measurement of energy in the International System is the joule. Momentum. The momentum q of a body is the product of the body's mass, m, and its velocity, v. The unit of measurement is kilogram times mass per second. The momentum is a vector quantity that has the same direction and sense as the velocity vector. It is particularly useful in the study of physical systems involving collisions. Momentum is one of those physical quantities that is difficult to understand, at least at first, because it cannot be tracked back to anything tangible. However, it becomes essential in the study of phenomena involving the collision of two or more bodies.
Imagine getting hit by a pillow versus a bowling ball. What's the difference? Momentum. Momentum is mass times velocity. The more mass or velocity, the more momentum. In a collision, momentum gets transferred. So, a fast, heavy truck has a much bigger impact than a slow bicycle. Understanding this is key in lots of areas, from sports to road safety. Hey everyone! Today, we're diving into some key physics concepts, showing you how they show up in everyday life. So let's get started. First up, let's talk about speed. Imagine you're in a car, cruising on the highway at 60 miles per hour. Speed isn't just about how fast you're going, but also the direction. So if you're heading north at 60 miles per hour, that's your velocity. Easy, right? Now let's move on to acceleration. Picture this. You're at a red light, and when it turns green, you hit the gas pedal. The car starts to pick up speed. That change in speed over time, that's acceleration. It's not just about going faster though. It can also mean slowing down or changing direction, like when you brake or take a turn. Those are both forms of acceleration. Next concept is force. You've probably heard of Newton's second law, F equals sine mr. Simply put, force equals mass times acceleration. Think about pushing a shopping cart. The harder you push, the more force, the faster it moves, the more acceleration. And if the cart's full of groceries, more mass, you'll need to push harder to get it moving. That's force in action. Let's talk about energy. Ever felt tired after running? That's because you used up a lot of energy. In physics, energy comes in many forms. Kinetic, that's the energy of motion. Potential, stored energy, and more. When you run, your body converts stored energy into kinetic energy. And when you stop, it changes back to potential energy. Energy is constantly being transferred and transformed in everything we do. Finally, let's discuss momentum. Momentum is mass in motion. Imagine playing basketball and dribbling the ball. The ball has momentum because it's moving. If you throw it, it gains more momentum because now it's moving faster. And if a heavier ball, like a bowling ball, moves at the same speed, it has more momentum because it has more mass. So, next time you're out and about, try to spot these physics concepts in action. They're all around us, making the world go round. Thanks for watching. If you found this video helpful, don't forget to like and subscribe for more awesome science content. See you next time.
Want to master physics in just 60 seconds? Let's dive in. Speed is how fast you're going. Easy, right? Now acceleration is how quickly your speed changes. Think of it like the turbo on a race car. Force, it's what makes things move or stop, like pushing a door open. More force, more movement. Energy is all about power. It can be kinetic when you're moving, or potential when you're waiting to move. Imagine a roller coaster at the top of a hill. Lots of potential energy ready to go. Momentum is the combination of mass and velocity. A big truck going fast, that's a lot of momentum. Got it? Use these concepts for your studies. Have any questions? Leave them in the comments below and hit the like button if this video helped you out.
Acceleration. Acceleration is a vector quantity and gives the rate at which velocity changes with time, in terms of both speed and direction. A point or an object moving in a straight line is accelerated if it speeds up or slows down. Motion on a circle is accelerated even if the speed is constant because the direction is continually changing. For all other kinds of motion, both effects contribute to the acceleration. X magnitude is measured in the SI as meters per square second. Energy. Energy is the quantitative property that is transferred to a body or to a physical system, recognizable in the performance of work. Energy is the capacity for doing work. Energy is a conserved quantity. The law of conservation of energy states that energy can be converted in form but not created or destroyed. Matter and energy may also be converted to one another. The unit of measurement for energy in the International System of Units (SI) is the joule (J). It may exist in potential, kinetic, thermal, electrical, chemical, nuclear, or other various forms. Momentum is the product of the mass and velocity of an object. It is a vector quantity possessing a magnitude and a direction. If m is an object's mass and v its velocity, then the object's momentum q is p equal m times v. In the International System of Units (SI), the unit of measurement of momentum is the kilogram meter per second, which is dimensionally equivalent to the Newton second. Physical quantities. Physical quantities are a characteristic or property of an object that can be measured or calculated from other measurements. Scalar quantity. Scalar, a physical quantity that is completely described by its magnitude. Examples of scalars are volume, density, speed, energy, mass, and time. Speed. In kinematics, the speed of an object is the magnitude of the change of its position over time or the magnitude of the change of its position per unit of time. It is thus a scalar quantity. The average speed of an object in an interval of time is the distance traveled by the object divided by the duration of the interval. The instantaneous speed is the limit of the average speed as the duration of the time interval approaches zero. Speed is the magnitude of velocity, which indicates additionally the direction of motion. Units of measurement. The units of measurement are the units that are used to represent physical quantities like length, mass, temperature, current, area, volume, intensity. There are different measurement units to represent the magnitude of the physical quantities, but in the scientific world, traditional units of the International Metric System are used. Vector quantity. Vector is a physical measuring that requires four things: magnitude, direction, sense of action, and application point. Magnitude has the numerical value and direction and sense of action to know which the numerical value is headed. Examples of vector quantity are force, velocity, acceleration, and momentum. Velocity. Velocity is the speed in combination with the direction of motion of an object. Velocity is a physical vector quantity. Magnitude, direction, sense of motion, and start point are needed to define it. The scalar absolute value of velocity is called speed, being a current derived unit whose quantity is measured in the SI as meters per second. For example, 5 meters per second is a scalar, whereas 5 meters per second east is a vector.